section 9.3. Alright, this is P series and harmonic series. Alright, let me look at, let me show you the form of the P series. Is sigma n from 1 to infinity, 1 over n to the p. So if you expand this summation, you're going to have 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and so on. Alright, this is the format of a P series. P here, it has to be positive constant. So it can be a whole integer, fraction, that's okay, but it has to be positive constant. Alright, we have a special case here when p equal to 1. So if p equal to 1, you're going to have 1 over 1, 1 over 2, 1 over 3, as I chose to you here, is harmonic series. Alright, and the general harmonic series is in this form. Let's go to the next theorem, 9.11, convergence of P series. So we know how the P series look like. Now you concentrate on the P, alright? If P is greater than 1, it's converges. If P is greater than 1, less than or equal, greater than 0, less than or equal to 1 is diverges, alright? So let's look at some example here. Alright, the first example, I have sigma n equal to 1 to infinity, 1 over n to the third. Look at our general form here. So you can see that my P here is 3. Right? My P here is 3. So it's greater than 1. So it's converges. We know that this series is converges, but I want to apply 9.10 from the previous section to show you that what is converges to. Alright? So I let this function be 1 over x to the cube. I can rewrite as x to the negative 1. As you can see, this is positive. The first condition satisfied is continuous. And if you want to check the decreasing function, you have to take derivative. I take derivative of this, negative 3 and x to the negative 3, the minus 1, which is negative 3 x to the negative 4. Obviously, it's less than 0 for all x greater than 1. So this function is decreasing. So I can apply 9.10. Alright. I take an integral of a function from 1 to infinity. As you can see, this is improper integral because I have limited of space. Normally, we will take a limit as a go to infinity and an integral from 1 to a. Alright. If you want to review that section, is in the previous lecture. Alright. So if I take an integral of 1 over x to the cube, I should have this function right here. And the upper bound is infinity, the lower bound is 1. Substitute the upper bound in here, you're going to get 0. Lower bound, you're going to have minus 1/2, which is 1/2. So this series is converges. We prove it by P series, and we use theorem 9.10 to show you that is converges to 1/2. Alright, so let's look at the example 2. I have a series sigma 1 or sigma n equal to 1 to infinity, 1 over n to the 1/2. Let's compare to our general form here. You can see that my P is 1/2, which is less than 1. So it's for in this section here, it's less than 1. So it diverges. Alright. Now P series says diverges, but I'm going to apply 9.10, which is an integral test, to show that is diverges to something. Alright. So I let my function be 1 over x to the 1/2. I rewrite it as x to the negative 1/2. You can see this is positive function as x greater than or equal to 1 is continuous. I take derivative of it. This is what I get, which is less than 0, so it's decreasing. So I can apply the integral test. Again, I take an integral from 1 to infinity, 1 over x to the 1/2. I skip the improper integral, but the result will be the same, alright, which is 2x to the 1/2, 1 to the infinity. My upper bound is infinity. If I substitute infinity into my x, I'm going to get infinity. Infinity plus 2 is infinity. So the series is diverges. Alright, so we finished 9.3. See you later for 9.4. Bye.